trying to stay warm.
So can you repeat that if it's cold?
Sure. This only works if it's a warm day, or if, well, this only works if the sun is out. If the sun isn't out, then it's just going to be cold, and I spend my 10 to 15 minutes walking around in circles or making little patterns in the snow or taking pictures of the snow or dancing around, doing whatever I can to stay warm.
So can you tell me how your research affects humans?
Let me see. This is bad.
I got just you in it, not the skidoo.
Okay. This is good. How does my research affect humans? Can't hear very well. All right.
So how does your research affect humans? Why should people care?
So what we're doing here in Antarctica is trying to understand how the West Antarctic ice sheet behaves. And the West Antarctic ice sheet holds a lot of water. So a lot of ocean water over hundreds of thousands of years has accumulated and is stored in the ice sheet. And as its volume changes, sea level is affected. So one reason why we care about understanding how the ice sheet works is so that we can try to make projections about future sea level change. So if the ice sheet is discharging more ice than is accumulating through snowfall, that's going to be a contribution to the amount of water that's in the ocean. Sea level will go up. If the ice sheet is storing more ice than it's discharging into the ocean, the opposite happens. Sea level would go down. And in this region where we're working, in the Ross Sea sector of the West Antarctic ice sheet, there are these fast-flowing discharge features called ice streams. And we know from some work that I've done with colleagues at the University of New Hampshire and the National Snow and Ice Data Center, places like that, that the ice streams sort of change their rate of discharge on sort of hundreds of years time scales. And the ice stream where we're working right now, Cam Ice Stream, ceased its rapid flow about 160 years ago. The ice stream just to the south of us shut off about 850 years ago and then turned back on 400 years later. So it's quite possible that Cam Ice Stream, the one we're working on right now it's accumulating more mass than it's discharging to the ocean. It's sort of it has a net lowering effect on sea level, but it could turn back on. And so we want to understand the processes that underlie that kind of behavior.
So that leads into another question that she wanted, which is, what are the different parts of a glacier? Or how about what are the different parts of an ice sheet?
Okay. So there are the ice sheets that exist on Earth today. There are three large ones. There's the Greenland ice sheet, the East Antarctic ice sheet, the West Antarctic ice sheet. And the Greenland ice sheet and the East Antarctic ice sheet are pretty similar. You could think of them as great big pillows of ice. They're pretty flat in the middle, and the surface of the ice sheet gets steeper and steeper as you go towards the coast. And as you move towards the coast and encounter those steeper surface slopes, the ice speeds up. So the rate at which it's flowing goes from a few meters per year to hundreds of meters per year. And the ice is then sort of funneled out through outlet glaciers into the ocean. In West Antarctica, the situation is very different. The interior part of the ice sheet has some fast flow features within it, and that allows the ice sheet to really efficiently move that ice that's accumulating in the interior out to the coast. So the ice sheet in West Antarctica is very different than in the East Antarctic, but in general, in the center of the ice sheet, we have what we call the accumulation area, or the net accumulation area. So in the wintertime, snow falls over the whole ice sheet, and in the summer, if it's warm enough for there to be melting going on, as is the case in Greenland, then some of that snow is lost to melting. Here in Antarctica, it's never warm enough for there to be much melting going on. So we don't lose any of that snow. It just keeps accumulating year after year. And the way that ice sort of leaves the system is by iceberg calving around the coast. In West Antarctica, when you move away from the interior of the ice sheet, in the part of West Antarctica where we are, the Ross Sea sector, the ice starts to speed up, and tributaries to features that we call ice streams form. You can think of these tributaries as being a lot like tributaries for stream systems in a terrestrial setting. And those tributaries, instead of flowing maybe 10 meters per year, the ice is flowing up to about 100 meters per year. Those tributaries come together into large discharge features called ice streams that flow many hundreds of meters per year. And all that ice is flowing down towards the coast. When it gets to the coast, as it gets thinner and thinner, eventually it gets thin enough to go afloat on the ocean surface. And when it does that, we call that transition zone between the ice that's resting on bedrock and the ice that's floating in the ocean, the grounding line or the grounding zone. And once the ice flows across that grounding line, if there is an embayment and there are lots of discharge features, all that ice that's discharging from the glaciers or the ice streams coalesces and forms what we call an ice shelf. And the ice shelf is just a floating kind of platform of ice. The ice is still flowing towards the ocean. It's still going down its own surface slope. And eventually, as the ice flows through the ice shelf, it gets to the seaward front of that feature and calves off as icebergs.